We're going to begin a study now of trig identities, and an identity is just something that's identical to another, just like the name suggests. If I say x plus x, I know that that's identical to, equal to, 2x for any value of x. Put any value of x into both sides, and both sides of the equation will be balanced. Here's a trig identity that we know already. We know that the secant of an angle is identical to 1 over the cosine of the angle, as long as the cosine of theta isn't 0. Well, cosine is 0. We know if we think of a cosine graph at pi over 2, 3 pi over 2, 5 pi over 2, etc. So this statement is true always as long as our angle is not pi over 2 times n, where n is odd. That's one way you could state the restriction. Or you could say, an equivalent way to say that is to say 2n plus 1. If you put integers into 2n plus 1, it generates 1, 3, 5. It generates odd values, pi over 2, where n is an integer. All right? So an identity, just to summarize, to emphasize, is an equation that's true for all values of the variable for which the equation is defined. Now, just while we're talking about identities, we should just compare that with what we call a conditional equation. If I were to give you x plus 2 is equal to 5, this is not an identity because this statement is only true for given values of x. In this case, it's only true if x is equal to 3. There are many trig identities. The first batch that we're going to look at are called quotient identities, and here's the one I'm going to bring out. Tangent theta is equivalent to, identical to, sine theta over cosine theta, of course as long as cosine theta is not 0, which we just said a moment ago was when theta is not n pi over 2 where n is odd. Alright, well the question is, how do I know that? We can't just assume that to be true, we need to show that. Well, if you remember, we have definitions for tangent, and that's the y-coordinate over the x-coordinate. And for sine, we know the definition is y over r, and cosine is x over r. And if I were to simplify the right side, y over r divided by x over r, which means to multiply by the reciprocal, I can see that I can show that the left side is equivalent to the right side. Alright, let's just talk a little bit more about this identity to get a feel for it. So what we're saying is this statement is true for any value of the variable as long as theta is not n pi over 2. So if I were to take, for example, 28 degrees, I should be able to show in my calculator that that's identical to the sine of 28 degrees over the cosine of 28 degrees. Okay? So I'm in degree mode, and I'm typing tangent of 28, getting that decimal, and the sine of 28 divided by the cos of 28 is an identical value. So I get the feeling of that by verifying numerically. I'm just putting numbers in to get a feel for this. Yeah, that looks right. If I took 56 and put them into all the places, it would be identical, as long as I don't pick one of the restricted angles. Another way to get a feel for an identity is a graphing approach. So what I'm going to do back with this identity is on my graphs, I'm going to put in one graph to be the tangent theta, or x graph. Now we know what that looks like because we've studied that. And then I'm going to, as a second graph, which will come up in red, type in the sine x graph divided by the cosine x graph. And what should happen is that the two graphs should be identical for all values. So let's graph 7. Comes my tangent graph. And I'm getting an identical graph, so that feels right. All right, so this is a way to get a feel as to whether two things are equivalent or not. If you graph them and they're identical graphs, that gives you a good feeling about that. If you test it numerically and you get the same values on both sides, that gives you a good feeling about it. But in terms of why it's true is what we just showed up above. We showed that both sides were equivalent to y divided by x. So we know for certain this identity is true. So if this identity is true, and we know that cotangent is the reciprocal of tangent, that would mean that cotangent is cosine theta over sine theta. Here's another quotient identity to know. The restriction on this one is that sine theta can't be 0, and sine is 0. Think of a sine graph as 0 at 0, pi, 2 pi, negative pi, so the angle can't be n pi, where n is an integer. We also have our 3 reciprocal identities, you'll remember. Now I'm just going to review this in a slightly different way. I just want you to remember that when we say reciprocals, that's 2 things that multiply to 1. So the reason, remember, that these 2 values are reciprocals is that if you multiply them, you get 1. So cosine and its reciprocal secant, they multiply to 1. So we have that identity, sine times cosecant is 1. They're reciprocal, so they multiply to 1. And tangent multiplied by cotangent. And with any of these identities, we could write them as we did before. For example, secant theta is 1 over cosine theta, as long as we're mindful of our restricted values. Okay, here comes another batch of identities. We're going to use our circle with radius r. Here's an angle, theta. Radius r, and we know that this point here is x comma y, which is x distance here and y distance here if I make a triangle. And I know that x squared plus y squared is equal to the radius squared. And if I divide both sides by r squared, that can give me x over r squared. I'm just doing a couple steps here. Dividing by r squared and writing it in bracketed form like so. So this is equivalent to this. And we know by definition x over r is the cosine. So cosine squared, y over r is sine squared. And when we have a square in that position, remember that's equivalent to saying cosine squared theta. It's the ratio we're squaring, not the angle. And here's an identity that's true. In this case, for all values of the variable, because there are no restrictions on sine and cos. So again, just to get a feel for what we're saying, if we took, again, 28 degrees and plugged 28 degrees in there and worked that out, verifying numerically just to see if it works out, the cosine of 28 squared plus the sine of 28, that should come out to 1. And it does. If I wanted to verify my identity graphically, then I type both sides in as their own graphs. So cosine x. Now ideally you would put that entire expression in brackets, but if you put the square there, it's not going to square the angle, it's going to square the ratio, which is what we want. So I'm good to do that. Plus sine of the angle, square the ratio, equals 1. Alright, so we should get identical graphs. We should get y equals 1, a constant function, since we know that function. Let's graph, and indeed we're going to. There's the left side, and there's the right side. Remember, verifying numerically and graphically doesn't prove the two things are the same, but it gives you a good feeling about it. The proof of it all, in this case, was what we did right here. Now that we know that this identity is true, by the way, what we often do is we move terms from side to side, and we can say things like, well, we know that cosine squared theta is identical to 1 minus sine squared theta. Okay? And we'll do that kind of thing quite a bit moving forward. But what I want to do next is I want to create 2 new identities using this result. So what I'm going to do to create the first one is I'm going to take my given expression and I'm going to divide both sides by cosine squared. So dividing all the terms by cosine squared. And that's going to reduce to cosine squared divided by cosine squared is 1. We know that sine divided by cos is tangent, and so this would be sine over cos times sine over cos. I can think of it that way. And so that would be the tangent squared And we know that 1 over cos is secant, so 1 over cos squared would be secant squared. And so we have a new identity, which is true as long as cosine is not 0. Okay, always mindful of our restrictions. And now let's take our result from above once again and do something different to it. Instead of dividing both sides by cosine squared like I just did, I'm going to divide both sides by sine squared. So dividing all terms by sine squared. So cos divided by sine is cotangent, we know that. So cos over sine times cos over sine, which is what this is, would be cotangent squared. Sine squared over sine squared would be 1. And 1 over sine would be cosecant. So 1 over sine squared would be cosecant squared. And so here's a third identity. So we have 3 Pythagorean identities in total. Our first one was this. Then we came up with that one. And then we came up with that one. Just a couple of examples to end the video. We have a trigonometric expression given. And we want to determine the non-permissible values in radians for each expression. And then express the following in terms of a single trig expression. All right. In terms of the restrictions, I always like to do that by thinking of all of my trig ratios in terms of sine and cos. So for example, tangent we know is sine divided by cos. Secant is 1 divided by cos. These are all multiplied together. And cos can stay the way it is. And when I get it in this form, I can see obviously I have a denominator of cos. So cos can't be 0. And so as we said before, theta can't be pi over 2 n, where n is odd. So there's my restriction. Okay. In terms of simplifying, in this case, converting to sine and cos is helpful because that allows me to reduce my terms. We're multiplying fractions, so we can cancel like that. And so I'm left with sine over cos, which we know is tangent. So this entire expression is identical to tangent. And of course, that's now obvious to me as well because we know that secant and cosine are reciprocals, so these two identities multiply to 1. That's an even faster way to reduce it. Here's another example. This one has squares in it, so that's a clue that possibly Pythagorean identities may be involved. But first, let's take care of restrictions. You always do your restrictions before you reduce. Cosecant squared, if I think of all of this in terms of sine and cos, I can think of this as 1 over sine squared. So I know that sine can't be 0. For this one, it would be cosine squared over sine squared. Again, we'd have a sine squared in the denominator, so sine can't be 0. And for tangent squared, that would be sine squared over cosine squared. Cosine's in the denominator, so cosine can't be 0. And remember, sine can't be 0 when theta is n pi. And cosine can't be 0 when theta, this is not, pi over 2n, where n is odd. Now, just a more efficient way to combine these, we're basically saying we can't have pi over 2, then we can't have pi, and we can't have 3 over pi over 2, and we can't have 2 pi. So basically every pi over 2 we're not allowed to have. So we could simplify this by simply saying, instead of that, let's just say theta can't be pi over 2n, where n is any integer. Now that we have our restrictions in terms of actually simplifying this expression, hopefully we'll notice that there's an identity that is similar to part of this. And that's this identity we proved earlier, that 1 plus cotangent squared is equal to cosecant squared. And if we rearrange that, we'll notice that this part, which is what we have right here, is equivalent to 1. So we can do that replacement, and then you need to recognize that 1 plus tan squared is another identity we proved earlier, which is secant squared.